Thanks everyone for joining us. Welcome to our next session for the secure and privacy in photography. What's happening?
I think I need to just. Yep, now it should go. Try.
Perfect. Great. Thank you.
Okay, perfect. So welcome back to our session on secure and privacy in AI and finance. So we are having Matthew Jagielski. He's a prominent research scientist from Google Brain. He has several publications in top security conferences. And his interest is in the intersection of security, privacy, and machine learning. So please.
Thanks so much. Thanks for coming, everybody. So as we're all aware, there's a lot of models being trained these days on sensitive data and sensitive applications. My Google actually trains models on emails, medical images, and text messages, all of these. And these are, this is training on sensitive data. And, when someone might be wanting to sort of tamper with the process, tamper with training, lots of bad things can happen in these kinds of applications. And I'm going to start the talk by sort of describing a little bit of what can go wrong when not everyone's behaving as expected. And to start, I'm just going to sort of, to make sure we're all on the same page, I'm going to give a brief outline of supervised machine learning. Here you essentially collect a data set consisting of data and labels from some users. You feed this into a learning algorithm, and then that learning algorithm spits out a model. And then this model is going to be used to produce new predictions on new data that it hasn't seen before. And you can break this up into a training phase, which is basically everything up until you get your last model. And then the testing phase, which is when you start to use your model in the wild. And there's sort of two parties involved here. There's the sort of people contributing data and the people, or the person that owns the model. And they each have their own sort of expectations for what's going on in this process. The first thing on the user side is that they want this model to be good for them. If this is like a fraud detection model, they don't want all of their transactions to start being classified as fraud. And so they want it to be useful for them. And they also want the model to be private. They don't want the sort of fact that this training process is happening to leak private information about their data. And then the model owner has also their own requirements. They require that the model is going to perform well on new data. This is basically, the point of doing machine learning in the first place. And they also, in many situations, are going to want their model parameters themselves to be private. They don't want someone to be able to sort of play with the outputs of the model and figure out what their parameters are, because they put a lot of work into building this model. And it turns out that adversaries that get into the mix can compromise these expectations, each of these expectations. One way they can do this is in what's known as a poisoning attack, where you can inject training data into the sort of training process of the model and corrupt it in a very specific targeted way. And then sort of an adversary who's doing what's known as an evasion attack, this is also known as adversarial examples, can modify their inputs into a model in order to evade it, in order to change the classification. You can think of this as sort of in a fraud detection model. You might sort of change a fraudulent transaction a little bit to sort of skirt around a model. And then someone might be able to analyze a model that's already trained in order to learn properties of the training data. This is known as an inference attack. And sort of to compromise the privacy of the model itself, someone can analyze the outputs of the model in order to learn sort of the parameters or learn a similar model. And I've done work in sort of each of these areas, but today I'm mainly going to be focusing on inference attacks on the training set and a little bit on poisoning. If you have any questions about any of the other ones, I'm happy to take that afterwards. And so right now I want to dig a little bit more into what these sorts of training data inference attacks can do. The sort of standard one that's considered a lot is known as a membership inference attack. And essentially in a membership inference attack, the goal is to determine whether some given target record was contained in the training set of a model. This was sort of originally considered for statistical data analysis back in 2008 and sort of extended to machine learning in 2017. This has been a very vibrant field of research since. And then something that's a situation where you might think that a membership inference adversary would be sort of scary is like in a medical application, for example, where maybe your membership in a training set means that you have a specific disease and you don't want people to learn all of your diseases. But a sort of more obvious violation of privacy is known as a training data extraction attack. So here on the right, there's actually this great XKCD where someone prompts a model that says, long live the revolution, our next meeting will be at, and then the model completes the docs at midnight on June 28th, right? And so somewhere in the training set, some revolutionaries were conspiring to meet on June 28th, and now this private information has been leaked to this person who probably doesn't like the revolutionaries. And this isn't actually just a joke.
Yeah, I think this was a question. Like,
Yeah.
okay, I guess we're gonna get to that. Like, more examples of that.
Yeah. Yeah. So it turns out we showed this in 2020 that there's a state-of-the-art language model known as GPT-2, and it does this. So we managed to pull out actually like people's contact information from this model. I'm not going to talk too much about this. Most of this talk will be focusing on membership inference, but like this is a thing that you can do for at least for some of the models that we're seeing being put out in the wild today. And so yeah, basically these things are kind of worrisome. And to the rescue comes this tool called differential privacy. So what is differential privacy? Essentially, it's a way of training models or a way of doing statistics. Basically what differential privacy says is that for any two databases that differ in one row, if you run a DP training algorithm, you shouldn't be able to distinguish between these two worlds where this one thing has changed things. And essentially what this says is also you can't do membership inference. If you remember in membership inference, we're trying to determine whether one target record was.
Sorry, the speaker is muted.
Yeah, the meeting is. Give me 1 second. Perfect.
Cool. Yeah. So basically, if you train a model with differential privacy, it protects from both this membership inference threat and this training data extraction threat. And there's a sort of technical detail in differential privacy, which is this parameter epsilon, which governs how well it's going to be protecting from this kind of attack. And really all you need to know for this talk is that a smaller epsilon value means that it's going to be harder to distinguish. It's going to protect better from attacks, but it's also constraining the model, the training process more. And so typically this means that your accuracy that you're going to get from this model is going to be worse. Okay, so in a world where the sort of accuracy level of a given epsilon is not very good, it's sort of turned into a little bit of a game of what epsilon are we actually going to set. And there's been a line of work that I think it ruined the clicking. But basically, there's now been a bit of a line of work that's just saying we should use attacks. We should run these privacy attacks, see how scary they are, and then we'll use this to guide our parameter settings. Thank you. And this is a thing you can do, but if you're in the room and you're maybe a cryptographer, this should scare you, right? Because essentially what we're saying is I'm going to give you some results of an attack, and I'm saying I can't break my thing. That means it's private, right? And sort of in cryptography, we all know that if someone comes up to you and says, "Look, I tried really hard. I came up with this cool new crypto system. I tried really hard to break it, and I couldn't do it," that obviously means it's secure, right? And so sort of this line of work, which I've participated in, is making this claim. And so the obvious drawback of this sort of line of questioning is that any attack that we might be using today to do this testing could be weak, and sort of tomorrow all the results from this kind of analysis could be invalidated. Another drawback is that essentially if you run these attacks and then you change the data set a little bit, maybe you collect a little bit more data, and this can actually drastically impact the performance of these attacks. And so today I'm going to be talking a little bit about how these poisoning attacks that I talked about before can actually really change the performance of membership inference attacks. And so sort of the threat model here that we're going to consider is an adversary who wants to learn whether a given target record was in the training set, but they're also capable of adding training data into the process. And so this might come up in like an MPC, for example. We're trying to train data on my data set and your data set. I'm going to add some data into my data set in order to cause the model that we produce together to leak information about your data set. And it turns out that if you give this adversary this extra power, it gets way better at privacy attacks. So I'm going to be talking today about giving you a little bit of a description of how this can improve membership inference attacks, but there's also these training data extraction attacks also improve. And then other attacks known as like attribute inference and property inference also get a lot better when you give this adversary this little more power. And all I'm going to be describing for now is how you can do this on k nearest neighbors, which is a very simple model. Essentially, any query that you give to this model, it will find the 3 closest data points in the training set, and then it'll just come up with the majority prediction on those 3 data points. So this green square that I'm pointing to, the 3 nearest neighbors are itself and then 2 other green squares. And so if you ask the model, what's the label of this green square, it will tell you it's a green square. And we're going to be trying to do membership inference on this green square down here. And it just happens that this green square is around a lot of other green squares. And so it turns out that if you remove this point from the training set, nothing about the model would change. You can't query it on any point and sort of observe that change. And so what this kind of means is that if we're trying to determine, we're doing membership inference to determine between the world where this point is contained in the training set and when it's not, you can't distinguish between these 2 worlds. This point has no influence on the model if you fix all the other points. And so membership inference here is impossible. But it turns out that if you add 3 points into the training set, it becomes perfect. The 3 points we're going to add are 1 point that's very, very close and is a blue circle, opposite class. We're going to add a green point that's also very, very close. It's the same class, so a green square. And then we're going to add another blue circle that's a little bit farther away, but closer than any of the other points in the training set. And so now if we look at our 2 worlds, the world where it's in, what we see is that the 3 points that are closest to this example are going to be itself, and then the 2 sort of split class points around it. So what we'll see is the 3 closest points, 1 is a blue circle, and then 2 are green squares. And so the class that you predict when it's in is a green square. And when it's out, this is no longer there to sort of break the tie. The example itself isn't there to break the tie. And so the close blue circle point is going to be the one that breaks the tie. And then you'll predict the class as a blue circle instead. And so here, this is a perfect membership inference attack. The class label that you get when you query on the point determines exactly what point, whether this point is a member. It turns out that actually, if you want to attack sort of like state-of-the-art neural network models, it's actually even easier, but I'm not going to get too much into this. Yeah, you have to be able to add points into the training set. There's no like sort of model in k-nearest neighbors. It's essentially just completely specified by the training set. Yeah. So this is kind of a bad property of a thing that we're doing to say something is private, right? Like if we change a couple points, we need to suddenly redo all of our suite of attacks. And so, you know, I'm coming to you today to tell you about a work that I do on sort of attacking models and sort of trying to estimate their privacy with attacks. And so I should think that this is a reasonable area despite these drawbacks, right? And so I'm going to describe a couple things that I think make this a really worthwhile direction for research. The first is that when you run one of these attacks, you get something very concrete. If you give me an epsilon for differential privacy, what this says is there is maybe a world in which sometime in the future, someone will come up with an attack that will get you this epsilon bar that differential privacy tells you it does. But if you run an attack and it says, I can determine whether this point is in the training set, that's a much more concrete thing. It's a lot easier to explain to people. And that's just like a nice thing to have. But sort of from a research perspective, rather than a sort of interpretability perspective, it also helps inform theory. So there's a couple of papers. I'll talk a little bit about the first one, where sort of you can sort of understand better your privacy parameters by running attacks. And the other thing you can do is find bugs by running these kinds of attacks. So if I tell you that a model is 0.2 differentially private, but then I can run an attack that gets essentially a level of epsilon equals 2, then this means that the sort of implementation or the proof of your privacy was incorrect. And we actually found a paper last year where we were able to run an attack that violated its privacy claims. And it turns out that this was the result of some just a sort of a bug in the code, which turned out to be quite important. And this is also something that I guess shows up in cryptography, right? You can have bugs in your code or sort of implementation details that aren't exactly in the math that can have really big impacts on how secure your implementation actually is. And so this is something that you can also do with attacks.
What do you mean by there was a bug in their code? Was it like in their proof, or what do you mean by code? What's code?
Yeah, so they like prove a theorem that says our algorithm is this level of differential privacy, but it turns out sort of in the implementation there was like an extra factor that basically meant that the number that they were that the analysis gave was going to be too big or too small.
You attack the code. That's what you did.
Yeah, so we ran their algorithm, tested its privacy, and found that it was less private than what the proof claims because of this mismatch between the code and the proof.
Code, and that's what you got.
Exactly. Yeah.
Isn't this model already trained and what?
Yeah, so this actually, why don't so this is something that you can do to audit the training algorithm itself. It's the best attacks that we know require you to be able to play around with the training algorithm. But actually, let me step one slide ahead and sort of describe how this setup kind of works for the kinds of attacks that we did to find bugs and help inform privacy proofs.
But this so you don't attack a particular model, you attack.
That's right. You attack an algorithm.
Yeah.
It's this is a kind of a technical detail, but this is pretty important. For example, differential privacy doesn't apply to a model. Differential privacy applies to the algorithm. Yeah. Okay. So the thing we're going to be looking at for this next little section is DPSGD. DPSGD is a very, very popular, widely used, very simple tool for private machine learning. And it adapts the standard stochastic gradient descent algorithm to satisfy the differential privacy constraint. And the way that it does this is it does two things. It clips the gradients of each example, and it adds noise. Clipping the gradients bounds the contribution of any one example to the final model, and adding the noise sort of obscures that contribution. So any one point is going to have a very small signal to noise ratio, but in the aggregate, they'll have a very good signal to noise ratio. And what we're going to be looking at is the sort of true level of epsilon for a given setting of your parameters. And the trick is, despite the very simple nature of DPSGD, it turns out we don't actually know what level of epsilon it really has. There's been a long line of theoretical work that's improved on the sort of level of epsilon for a given setting of the parameters. You run the exact same code, and sort of over the years, we've learned that this code has an epsilon that's like 1,000 times less than what we knew it was in 2013. And so if you're in this world, it may be, let's say you're in 2013 and you train a model that's one differentially private, and then suddenly you learn that it's actually 0.001 differentially private. You're going to be a little bit like, why didn't I just train it with the one that in the future? And so you're going to be a little bit like optimistic maybe about how private it is. You're going to be like, okay, it's okay to train with 10 because tomorrow we might end up having a better analysis, and I might be in that world where I actually have one, but we just think right now that I have 10. And so you get this sort of epsilon creep. And one way to counteract that is by actually running these attacks. This is something that you can do to sort of learn what a lower bound on privacy is, because epsilon DP guarantees some level of attack effectiveness. It will bound attack effectiveness. If you run an attack and get a certain level of effectiveness, this bounds from the bottom, it bounds differential privacy.
But if this reason that in practice people are already thinking that the epsilon is smaller than what they.
Yeah. So yes. I think that honestly, as someone who does attacks, I think that we're probably being a bit optimistic. Yeah, so it's pretty common to use an epsilon larger than what you would be okay with, sort of based entirely on its theoretical guarantees.
So that's basically explains why some like companies are using like larger epsilons like previously, claiming that they're like data analysis that we're extracting from users' activities on the phones, right?
Yeah.
They're having it 10, but they realize that with your attacks, basically that number is very efficient to deploy.
Yeah, and actually, like so we have at Google, like we have differentially private training that Peter will talk about in more detail, but also the US Census, I think, used an epsilon that's like something like 10, which provides basically no provable privacy guarantees just based off of that number. But like they sort of have some intuition for why it's actually better. It's just essentially this idea. There's a gap between the best known attack and the best analysis. Sort of in the thing that I'm going to describe in a second, basically we're going to show how you can improve on sort of the best known attack that we have by a pretty significant factor, tighten this gap between the best attack and the best analysis. And we're actually going to do this with poisoning attacks, which we talked about earlier. And we're going to use them in quite a different way. And so what we're going to do is we're going to start with our original data set. So this is the thing we want to know, how private is it? We're going to add some poisoning to the data set. So we're going to run a good poisoning attack. Doesn't really matter exactly, look at the paper for exactly how the poisoning attack should be generated and stuff. But basically now we have two worlds. We have the world where the data set's not poisoned and the world where it is poisoned. And then we're going to train our model, or we're going to run our epsilon DP training algorithm many, many times on both of these data sets. And we're going to measure how effective was that poisoning. And basically, the poison database should be the one that produces more effective poisoned models, because that's what the poisoning is designed to do. But it turns out that if you sort of try to distinguish between these distributions, between the sort of worlds where it's poisoned and not poisoned, you'll be able to get some effectiveness of this distinguishing. And then essentially what that's saying is we can learn whether that poisoning was in the training set or not. We're leaking the privacy of the poisoned example itself and getting sort of an estimate of how private the model is. And we're going to sort of not look too deeply into this slide, but essentially here on the x-axis, we're going to be plotting the provable epsilon, the upper bound from the proof of privacy. And the y-axis is going to be the sort of lower bound that we get. And the sort of state of the art before this paper is here on this red line, and our technique is on the green line. And then this blue line here is just y equals x. It's essentially the line where the analysis. The closer we get to that is better. And so for sort of these smaller epsilons, like we have a huge improvement over the existing attacks, and factor of 10 of epsilon. So we were in a world where essentially the gap was 100 or more. So you might be optimistic by a factor of 100 in your sort of epsilon creep, and then we get into a world where the gap is less than 10. And in a setting where this epsilon has changed by 1,000 or so in the past 6 years, getting down to a range where we know it's in a sort of factor of 10 is quite nice to have. And so essentially this tells us that our epsilon is getting close. The proofs, there's not much more that can be done in the analysis, and it gives us a much better sense for actually what epsilon we should be using in practice. And in our paper, we also looked at a couple different assumptions that might be able to improve the analysis and sort of tighten this gap. And with that, I'd like to thank you all for coming and listening to my talk. And feel free to ask any questions. Thank you.
So let's see if there's any questions here in the audience. I keep checking the online. There's people on Zoom.
We want to ask you to, so I understand you're bringing up the lower bound.
Yeah.
Right. Yeah. Are there people bringing down the upper?
Yeah, absolutely. I think actually Peter might end up talking about this a bit for some applications, but like There actually was some work more recently that where essentially depending on what assumptions you make on your adversary, the bound is essentially tight. So really all that we can do at this point is improve attacks now. And this is quite a strong attack. I think if you told someone that this like if I'm going to add poisoning and then train a ton of models to distinguish, you know, whether this poisoning was in the data set, they would think like this is already a strong adversary. And so we're kind of in a world where now we need to take the attacks and get them from like these very, very worst case settings and make them into things that you might be more likely to be able to run. And yeah, but
what does it mean to have a tight upper bound if it's not that we have an attack?
Yeah, so the tightness is basically this is a little bit details, but in the analysis, essentially for DPSGD, you assume that you get to see every single intermediate model update, at least in one version of the analysis. And it's hard to sort of get just the last model, which is really what you're releasing at the end of the day. If you allow an attacker to sort of control everything about the process and see every single intermediate model update, then it's a tight analysis. But this is not really close to something that you get in the wild when you're trying to run attacks. And so the question is there something about, you know, sort of only releasing the last update or the last, you know, couple updates or something that makes this provably better? This is one thing you might get. It's difficult to say this for like in general models, but yeah, there's like things now that we can think about improving the attacks in this way that sort of get closer to what the really, really, really worst case is, and also improving the assumptions that you make in your analysis to get into a world where it's more likely to match a realistic attack. Yeah, thank you.
So thank you so much, Matthew. Since oh, you have a question?
Yeah, so do you think you know, highlight the data poisoning? So
Are you saying like this is a good reason to use synthetic data as you?
yes, now this can highlight the risk of
So the risk of synthetic data is that it might be poisoned?
I mean, the synthetic data is actually that would be even more effective data.
I see. Yeah, it's possible. I mean, the thing is like when you're coming up with your synthetic data, if the data that you started with was poisoned, it might sort of also propagate into the synthetic data, which yes is definitely a risk, and something to be careful about. I don't know if anything I've talked about necessarily has implications for synthetic data, but it's reason to be worried at least about this.
Is there a way to detect that there's a poisoning going on or not?
This is a very big question, and it depends a lot. I only talked about sort of poisoning that's designed to make privacy more obvious. There's a lot of different things that people have considered for what a poisoning attack might be designed to do, and detecting that is very dependent, at least, you know, for now, on what it's designed to do.